Introduction to Electric Vehicles. I'm your instructor, Dave Semelink from Go Digital SA Foundation. In this course, you will learn about electric vehicles, or EVs. You do not need to know coding, but we will talk about electronic control systems and how they use code to control a vehicle and to define its characteristics. This course will cover, in Unit 1, the overview of ICE vehicles and electric vehicles. In Unit 2, we'll have an overview of electronic vehicle control systems. And in Unit 3, we'll talk about jobs in a post-ICE world. Units 4 to 7 are optional labs where we will look at the specific control systems. So today we'll do Unit 1, overview of ICE and electric vehicles. So what is a vehicle? From Wikipedia, a vehicle is a machine that transports people or cargo. Vehicles include wagons, bicycles, motor vehicles like motorcycles, cars, trucks, and buses, railed vehicles like trains and trams, watercraft like ships and boats, amphibious vehicles, screw-propelled vehicle or hovercraft, aircraft, airplanes and helicopters, and spacecraft. In this course, we are mainly covering land-based vehicles, and we're going to exclude motorcycles. So in other words, cars, vans, trucks, and buses. The first land vehicles used some type of ski or skates and were originally pulled by people and later by animals, like horses, camels, oxen, and so on. Wheels eventually replaced the skis. Okay, so the very first vehicles were just dragged across the ground. And then later on, wheels were invented, which worked a whole lot better than skis. Animals have lots of drawbacks: feeding, housing, limited power, cleaning up after them, and so on. So when the steam engine was invented in the 1700s, people soon began making vehicles powered by steam engines. A steam engine is an example of an external combustion engine because heat produced by burning coal is used to make steam outside of the engine itself. So it's an external combustion engine. Steam engines were big and heavy, so while they suited railroad trains and ships, they were not very practical for smaller vehicles. Okay, so this is an early steam-powered car, and this is another one. The first practical car was invented in 1881 and was driven by an electric motor powered by batteries. These were the only type of cars for a few years. Okay, so these very early cars are electric. They had batteries that had to be recharged. And as you can see, here is a bunch of different electric cars that were available around that time. The problem with electric cars back then was the range and the ability to charge the batteries. In 1885, the first practical car with an internal combustion engine was invented. Liquid fuel, diesel or petrol, allowed a longer range than electric cars, so ICE cars quickly replaced electric cars. It took 100 years until in the 1990s, batteries and other technology improved to the point where electric cars were practical again. So again, we can see way back in the 1880s, here's a bunch of electric cars being charged. When the first internal combustion engine driven car was created, it quickly replaced the electric cars because it had a much longer range. And then finally in the 1990s, electric cars started appearing again. Starting in the 1990s, the benefits of electric vehicles became obvious. They do not pollute. ICE engines produce poisonous exhaust that is a large contributor to climate change. They can have a lower total cost of ownership, or TCO. While an EV is currently more expensive than an equivalent ICE car, the fuel, the electricity, is far cheaper per kilometer than petrol or diesel. So if you drive a lot, you're going to end up saving money. The cost to maintain them can be much cheaper because they have fewer parts that need maintenance. So again, if you keep it for a long time, it's going to be cheaper. The cost to make them is going down every year. The battery is the most expensive part, and advances in battery technology is making them cheaper. smaller, and lighter. As a result, EVs are becoming very popular and will outnumber ICE vehicles within the next decade or so. ICE vehicles will eventually be banned because of the pollution they produce. Okay, these are just some examples of new EVs. That's a Nissan Leaf, that's a Renault Zoe, and that's a Tesla Roadster. Cars today consist of an engine for an ICE vehicle or a motor for an electric vehicle, and the drivetrain. That's what makes it move. Brakes slows it down or stops it. Steering makes it turn. Suspension, which is springs and shock absorbers, that smooths the ride when the road is bumpy. Electrics, headlights, taillights, brake, turn, and reverse indicators, the radio, the air conditioner, and so on. The car body, that's the shell that contains the doors, the windows, the seats, the bonnet and boot, or the hood and the trunk, and so on. And the chassis. Everything sits on top of or is connected to the chassis. Okay, an engine. ICE vehicles are driven by either a petrol or diesel internal combustion engine. A 4-stroke petrol engine contains one or more cylinders. Inside each, a piston moves up and down, moving a connecting rod up and down, which causes the crankshaft to rotate. A flywheel on the crankshaft gives it enough momentum to spin smoothly. A small electric motor is used to start the engine. Cams on the camshafts cause valves to open and close at the appropriate times, and a distributor sends high voltage pulses to the spark plugs at the appropriate times, causing them to make a spark in the appropriate cylinder. Okay, so this is a photo of the outside of a typical engine. You can't see much here. You can see the flywheel, and as you can see, this is a heavy wheel, so once it starts spinning, it wants to keep on spinning. And this is what's inside the engine. So this is a starter motor, which is used to start the engine. It's got a crankshaft with a flywheel at the end. You've got connecting rods that connect the crankshaft to the pistons. And then at the top, you've got input and output valves, and you've got spark plugs. You've got camshafts. As the camshafts turn, the cams push the valves open and closed. And here's the distributor, which, as it rotates, it sends sparks to each cylinder at the appropriate time. The 4 stages of a 4-stroke engine consist of, the first one is the outlet valve closes, the inlet valve opens, and a mixture of petrol and air is sucked into a cylinder by the piston moving down. Okay, so here you see the outlet valve is closed, the exhaust valve. The inlet valve is open, the piston is moving down, and that sucks a mixture of air and petrol into the cylinder. Next, the inlet valve closes and the piston moves up, compressing the mixture. Okay, so here, the inlet valve is now closed, the piston is going up, so it compresses the mixture of air and petrol. Next, the spark plug fires, and the exploding mixture pushes the piston down, which causes the crankshaft and flywheel to rotate. Okay, so here the spark plug is fired, there's an explosion that pushes the piston down, and that causes the crankshaft to rotate. The outlet valve opens and the piston moves up, pushing the exhaust out. Okay, here the piston is going up again, and it pushes the exhaust out. The exhaust valve is open, allowing the exhaust to go out. To control the speed of a petrol engine, you use the accelerator pedal. Pressing down speeds up the engine, releasing it slows it down. The accelerator pedal is connected via a wire to the throttle valve in the carburetor. The carburetor mixes petrol with air. The valve is normally almost closed, allowing in a small amount of the air-petrol mixture so the engine can idle when your foot is not on the pedal. When you press the pedal, the valve opens, allowing in more of the air-petrol mixture. Note that the carburetor has an air filter to keep out dust from the air and a fuel filter to keep out dirt from the petrol. Both need to be replaced periodically. Also note that some petrol engines now use fuel injectors instead of a carburetor. But the concept is the same. Controlling the amount of the air-petrol mixture controls the speed of the engine. Okay, so this is a photo of a carburetor. Here's an inlet for the petrol. So there's a pipe from the petrol tank that feeds petrol into here. This is a small tank with a float in it that fills up with petrol. That's over here. The petrol has a little pipe that goes into here, and as air is sucked in, the petrol mixes with the air. The throttle valve controls how much of that mixture gets into the cylinders. A diesel engine is similar to a petrol engine, but uses diesel fuel instead of petrol and has some differences in the design. The inlet valve opens, the piston goes down, sucking in air, the piston goes up, compressing the air, then a fuel injector sprays fuel into the cylinder and the mixture explodes without a spark plug. The heat of the compressed air causes it to explode on its own, pushing the piston down. Finally, the outlet valve opens and the piston moves up, pushing the exhaust out. Diesel engines have higher compression than petrol engines, so that the compressed air becomes hot enough to ignite the fuel, and therefore they don't need a spark plug. Okay, there are some other types of engine, but the concepts are basically the same. Two-stroke engines are often used in smaller vehicles like motor scooters. They're also used on lawnmowers and so on. They pollute more than four-stroke engines and they make more noise. That's how a two-stroke engine works. A Wankel rotary engine has a very different piston and cylinder, but it still burns fuel and air. So this is how a Wankel rotary engine works. You can see it's very different from regular engines, but it still uses petrol and air and causes that to rotate. Internal combustion engines have many problems. They have a lot of parts which need periodic maintenance. They have a limited speed range. As a result, a transmission or gearbox is required to give them a wider range. For slow speeds, the gearbox is set in first gear. Then as speed picks up, it must be shifted into second gear and so on up to the top gear. To match the speed of the engine to the speed of the gearbox, the engine needs to be disconnected from the gearbox when shifting gears. A clutch is used for this. So whenever you shift gears, you need to push on the clutch to disconnect the engine from the gearbox. Clutch plates need to be replaced periodically. The engine only rotates in one direction, so the gearbox also needs to have a reverse position to allow the vehicle to move in reverse. A carburetor is required to mix the fuel with air before it can be sucked into the engine. Carburetors require some maintenance to continue to work correctly. Some petrol engines use fuel injectors similar to diesel engines instead of a carburetor. The engine makes noise, so a muffler is needed on the exhaust pipe. Mufflers need to be replaced periodically. Engine routine maintenance includes replacing the spark plugs, fuel filter, air filter, engine oil, oil filter, transmission fluid, muffler, exhaust pipe, and clutch plates. This means an ICE vehicle needs periodic, potentially expensive maintenance. The engine is normally left running when the vehicle stops, for example at traffic lights and in traffic jams, wasting fuel and causing unnecessary pollution. But the main problem with all ICE vehicles is that they produce pollution. The exhaust contains both toxic components, which are bad for the health of humans and animals, and greenhouse gases, which cause climate change, and this has been causing serious problems for everyone on the planet for some time. These are some of the toxic components of the exhaust. So the emissions of various sources using petroleum fuels in kilograms per ton of fuel. Okay, so you get carbon monoxide, which is worse in petrol engines than in diesel engines. Nitrogen oxides, especially nitrogen dioxide, which is worse in diesel engines than in carburetor engines. Sulfur oxides, okay, which is worse in diesel engines. hydrocarbons, which is about the same in carburetor and diesel engines, organic acids, which are worse in diesel engines, and particulate matter. Those are the little specks of dust, the little black specks that you'll see making the exhaust pipe black and leaving black marks on the roads. And that's worse in diesel engines. The exhaust gases contain more than 200 toxic chemical compounds. Of these, the following are the most harmful substances. Okay, I'll just go through the list quickly. You have carbon monoxide, hydrocarbons, oxides of nitrogen, oxides of sulfur, solid particles, especially the black carbon particles, lead compounds, aldehydes, and benzopyrene, a harmful carcinogenic. That means it causes cancer. In addition to the direct negative impact on health of the person, emissions of the motor transport have greenhouse and ozone depleting effects on the atmosphere of the Earth. So again, petrol engines and diesel engines, nitrogen, oxygen, water, those obviously aren't problems. Then carbon dioxide, carbon monoxide, nitrogen oxides, sulfur oxides, hydrocarbons, aldehydes, soot or particulate matter, and benzopyrene. So these are the main greenhouse gases. Carbon dioxide, that's the main component in the exhaust gases of the engine. It creates a greenhouse effect in the atmosphere. Okay, greenhouse effect is what is causing global warming. The atmosphere is getting warmer because the carbon dioxide acts like a blanket around the Earth. Then we got methane, which is also a greenhouse gas, ammonia, and nitrous oxide. So these are all greenhouse gases. Some countries have laws to reduce the pollution from ICE vehicles, but pollution can't be eliminated completely. Also, as engines get older, they pollute more, especially if the engine is not maintained properly. Many car owners do not spend the money to maintain their vehicles properly, so you will see cars and trucks that produce visible smoke from the exhaust pipe, in addition to the invisible gases. And just keep in mind that a lot of these gases in the exhaust are invisible. You can only see some of the gases, but many of them are invisible, but they are polluting and they are causing global warming. For this reason, governments are making laws to phase out ICE vehicles. Various countries will ban manufacturing ICE vehicles by 2025 or 2030 or 2035. So just note, these dates are soon. This is going to happen very quickly. Let's take a look at the electric motor. So how is an electric vehicle different? An EV replaces the engine, carburetor, clutch, transmission, exhaust pipes, and muffler with one or more electric motors controlled by a computer. Instead of using petrol or diesel, it uses electricity supplied by a battery. The battery in a battery electric vehicle, or BEV, is usually very big to give the vehicle enough range. The battery can take up most of the underside of the car. It is usually positioned below the floor. Okay, so if we just take a look here, this is the battery. So it's a very large battery. And this is what gives it range. If you have a small battery, you can only go so many kilometers, but with a bigger battery, you can go much further. A hybrid EV, or HEV, has both a petrol engine and an electric motor. This allows the battery to be smaller. HEVs were popular when batteries were big and expensive, but are quickly losing favor to BEVs since the batteries are getting smaller and cheaper. Okay, so this is now a hybrid EV. It's got both a petrol engine and an electric motor, and so the two can take turns driving the car, depending on how far the battery is charged. But these still exist, but it's losing favor because batteries are getting cheaper and smaller. The electric motor has just two parts: the stator, which consists of coils of wire and does not move, and the rotor, which consists of magnets or metal that has an induced magnetic field and which can rotate inside the stator. So if we look at this picture here, we can see stator is on the outside, the rotor is on the inside. Okay, and with a changing magnetic field made in the coils, the rotor will turn. This diagram shows in detail how this works. So our rotor on the inside has got a magnet built in. So if we run a current through just this coil and this coil, it will cause the north pole of the magnet on the rotor to point up and the south pole to point down. Then we run a current through this coil and this coil that will cause it to turn. So now the north is here, the south is there. Then this coil and this coil. So it turns again. So the north is here, south is there. And then we run the current backwards through these two coils. So now the north points this way and the south that way, and so on. So by continuously pulsing these coils, it causes the rotor to turn. The controller sends pulses of current through the coils, creating a rotating magnetic field which causes the rotor to turn. Changing the speed of the pulses determines the speed of the motor. Changing the order of the pulses changes the direction. So if we want this rotor to turn the other way, we simply pulse it in the opposite direction. So we first pulse this one, then this one, then this one, then we pulse this, this, and this in the opposite direction, and that causes it to turn the other way around. The accelerator pedal in an EV is an electrical control, like a guitar effects pedal or a sewing machine speed pedal. Okay, you see these two pedals, these are electrical controls. When you push the pedal up and down, it changes an electrical signal. It sends a signal to the EV's computer telling it how far the pedal is pressed. The computer then controls the motor or motors to change the speed. Okay, so in an electrical vehicle, here you've got the accelerator pedal. You push down on the pedal, that changes the signal, which goes to the computer, which controls the motor by sending different signals to the motor. How does an electric motor compare with internal combustion engines? They have very few parts, so they need less maintenance. They can last decades without any maintenance. Okay, and typically the things that you replace in an electric vehicle are windshield wipers and very rarely the brake pads. They do not need a transmission. They can go from stop to full speed without one. As a result, they do not need a clutch. They can rotate in either direction, so they don't need a gearbox with a reverse position. A carburetor isn't needed. The motor makes almost no noise, so a muffler isn't needed. In fact, EVs are so quiet, some countries require that they have something to make a sound effect so that people know when they are close by. The motor stops when the vehicle stops, for example, at traffic lights and in traffic jams, so no energy is used when it isn't moving. They also have an incredible trick. To slow down or stop the vehicle, regenerative braking is used. This generates electricity, which is used to charge the battery whenever the brakes are applied. This also means that brake pads do not need to be replaced as often. And they have another trick. The characteristics of the motor is determined by the computer software. Since the software can be updated over the air via Wi-Fi or GSM data, the characteristics of the motor can be changed over time, improving the way the motor works and adding new features. Another advantage, the large battery under the car gives EVs stability. An EV will not flip over in an accident as easily as an ICE vehicle. ICE vehicles have a tank for petrol or diesel which can catch fire and explode in an accident. The battery of an EV can catch fire, but this has been shown to be about 10 times less likely, and they don't explode. An EV can have an electric motor directly connected to each wheel. This not only makes the design simpler, but wheels can be made to turn at different speeds, enabling better traction, and even in opposite directions, enabling a 360-degree turn, which is sometimes called a tank turn, which is impossible in an ICE vehicle other than a tank. Okay, as you can see here, this truck is going in circles without moving forwards or backwards. What's happening is the two wheels on the one side are going in reverse and the wheels on the other side are going forward. So that causes the vehicle to turn without moving. Okay, the brakes. Most cars have disc brakes on the front wheels and drum brakes on the back wheels. Some will have combined disc and drum brakes on the back. Disc brakes are usually hydraulic. The brake pedal is connected by a solid rod to a piston in the master cylinder. When you press on the pedal, the piston compresses brake fluid inside the cylinder, which compresses brake fluid in the brake hoses, which pushes a piston in each of the brakes. These pistons squeeze calipers, which force brake pads against the brake discs, slowing the wheels down. Okay, so here we've got a car where you can see there's the brake pedal. It pushes onto the master cylinder. There's hoses going to each of the disc brakes. So when you push on the pedal, it compresses the fluid. The fluid then pushes into the brakes. It pushes on a piston, which then pushes on brake calipers, which squeeze the brake pads against the disc. Okay, and that slows it down. In this example, the rear wheels have got combined drum and disc brakes. So the discs in the back work the same way as the discs in the front. Okay, in this example, we've got drum brakes in the back and disc brakes in the front. The parking brake is operated by the parking brake lever. When you pull it up, it pulls on cables. These cables cause the brake shoes to push the pads against the insides of the drum. So this is used to stop the car. Okay, normally when you stop a car, you pull up the lever so that the brakes keep it from moving. Okay, some EVs use the same mechanical brake system as ICE vehicles, but other EVs have regenerative braking. In these, taking your foot off of the accelerator has the same effect as applying the brakes. But instead of using the brakes, the motor is used in reverse to generate electricity. This causes the motor to exert a force that slows down the vehicle. It also uses the generated electricity to charge the battery. As a result, if you take a long trip down a hill, you can arrive with more energy in the battery than when you started. Using the accelerator pedal to slow down as well as to accelerate is known as single pedal driving. You almost never need to use the brake pedal. Okay, so as you can see from here, when you hold it in the center, it maintains speed. It accelerates when you push it all the way down. And when you let go, it applies regenerative braking. Regenerative braking operates like this. The battery supplies energy to the motor controller. This causes the motor to turn and the wheels turn. When you apply regenerative braking, the motor controller tells the motors to now act like generators. This puts a force on the wheels that slows the vehicle down, and that turns the motor, which is now operating like a generator, and so it generates electricity, and that is used to charge the battery again. In most vehicles, the front wheels are turned to change the direction the vehicle moves in. This is done by turning the steering wheel. This turns the steering shaft, which turns a toothed gear, the pinion, that pushes a bar, the rack, from side to side. This then pushes or pulls tie rods, which cause the wheels to turn. Okay, so you turn the wheel, that turns this shaft, that causes a pinion, it's a little gear, to cause the rack to move left or right, and that moves the tie rods, which turn the wheels. Most cars today have power steering to make it easier to turn the steering wheel. Sensors detect which way you are turning the wheel and cause a motor to assist with turning the wheel, or a pump pushes power steering fluid, similar to brake fluid, to help turn the wheel. Okay, so with power steering, you've got a pump or a motor. In this case, we've got a pump pushing steering fluid into the steering system, which causes the wheels to turn. Some EVs steer by wire. That is, the steering wheel is not connected to the wheels, but instead sends a signal to the computer telling it how to steer. The computer then controls the steering motor or pump to turn the wheels. Some ICE vehicles also steer by wire, but it's not so common. Okay, so in this case, we've got the steering wheel, which creates a signal which causes electric control units to tell the steering system how to steer. So in this case, there's no connection between the steering wheel and the actual wheels. Car suspension. If the wheels of a vehicle were directly connected to the chassis, the ride would be very bumpy. You can see this when you push a wheelbarrow, for example. So instead, they are connected via arms that can move up and down, and a spring and shock absorber, or damper, that allows the wheels to move up and down with the road while the chassis stays more or less level. Okay, so in a suspension system here, here we're showing the back wheels. They're connected to arms, and the arms are connected to the chassis. So they swing on the joint here, which means they can move up and down together with the wheels. We've then got springs and shock absorbers, which cause the chassis to move up and down more smoothly. If you look at this diagram, you can see that the wheels are bumping up and down with every bump in the road, but the vehicle itself is moving much more slowly. It also goes up and down, but much less, because of the actions of the springs and the shock absorbers. Some cars have active or electronic suspension that allows the controller to use sensors to adjust the dampers so the body can be nearly perfectly level while the wheels bump up and down. Okay, so in this case, we've got dynamic stability and traction control, where the damper, it's continuously controlled damper, causes the vehicle to stay more or less level while the wheels are bumping up and down. Okay, most EVs have conventional suspension. However, because they already have a computer and many of the sensors required for active suspension, it is less expensive to include them in an EV. In addition, some EVs use motors for the active suspension, and just like with the main motors, these motors can convert the energy of the bumps back into electricity to charge the battery. So they not only smooth the ride, but they help reduce the energy consumption of the vehicle. Okay, so here we've got linear motors. They can make the wheels move up and down. So if you're driving along and then you hit a dip, they will push the wheel down into the dip so that the body of the car stays level. And then if you hit a bump, the bump pushes the wheel up. That generates electricity in these motors, and that electricity is used to charge the battery, while at the same time not making the body jump up. Okay, electrics. The electrical system of a car consists of everything that uses electricity: lights, radio, air conditioner, and so on. Devices that use a lot of energy require thicker wires, while devices that don't use as much use thinner wires. A conventional ICE vehicle can have kilometers of wires to connect everything. Wires have to run from the battery to the fuse box, and then to the switches, and finally to the devices. So for example, and you can see this diagram shows all the wires in a car. The lights in a car include 2 headlights, each with high beams and dipped filaments, 4 parking lights, 2 in the front, 2 in the back, 4 turn indicators, 2 in the front, 2 in the back, and there could be more on the sides and on the mirrors, 2 reverse indicators, 2 brake lights. Usually there's also one in the top middle of the back, and interior lights, including the glove box. So you need wires running to all of these lights. To reduce the number of wires, a system called the CAN bus was developed in the 1980s to control electrical devices electronically. Instead of running wires from each switch to each lamp, a module with, for example, the left headlight, turn indicator, and parking light would instead have 1 thick power wire and 1 much thinner signal wire. And the signal can also be combined with the power wires, so only 1 wire is required in addition to the ground or chassis connection. The signal tells each light if it should be on or off. So now you've got one wire going to the headlight, which has dipped and high beam filaments, and to the indicator and parking lights. So just the one wire goes to each of them, and then electronics will tell which one is meant to be on and which ones are meant to be off. Okay, so this system is common in all types of cars now. It's not in all cars, but quite a few cars, including ICE engine cars. And the main reason is to simplify the wiring. Okay, you can see from this diagram, in the old days, or without the CAN bus, you have wires going all over the place. With CAN bus, you can have just one wire, and all the different devices connect to that one wire, and then they listen to the signal, which tells them if they should be on or off. It allows centralized control. So here we've got one controller controlling everything that's on the bus. Okay, and it's robust and it's efficient. Okay, in fact, CAN bus lights and other devices are now available with the controller electronics built in. A vehicle designed with CAN bus will use these instead of regular lights. This now is a headlight, and you've got the high beam and the dipped light here, and it's got an electronic controller, and you can see here it says CAN bus. So when you plug this thing in, it listens for CAN bus signals, which is telling it, should it be off, or should the high beam be on, or should the dipped beam be on. Because EVs already have a computer, the CAN bus is easy to include. The computer controls all electrical devices in the car. The CAN bus in an EV controls more than just the lights and other electric devices. As we will see later, it can control every aspect of an EV. Okay, so here's an EV. We're not talking about lights here, but you can see there is a CAN bus controlling how all these different devices in the EV work. So it's already got a CAN bus, and now you can use it for everything. The car body. There's no difference between an ICE vehicle body and an EV body. However, because EVs try to reduce the load on the motors to extend the battery life, EVs generally have a more aerodynamic shape to reduce drag coefficient or wind resistance. Okay, sports cars have always had a low drag coefficient so that they can go faster. Regular ICE vehicles don't bother with this since most people don't really think about the cost of petrol. Small EVs that are meant for city driving also don't bother with drag since they rarely go fast enough for it to make a difference. Here's an ICE engine sports car. And it's got this body shape so that the wind resistance is as low as possible so it can go fast. This is an electric vehicle. This happens to be a three-wheeled vehicle, but it's an electric car. Its shape was made so that there's as little drag as possible so that the battery doesn't run down so fast. And here's another electric vehicle, and same thing. They've designed it so that the drag is as low as possible so that the batteries last longer. The chassis is a frame that holds all the parts of the vehicle together. An ICE vehicle chassis holds the engine, drivetrain, wheels, suspension, and the car body. An EV chassis holds electric motors, batteries, wheels, suspension, and the car body. Okay, so this is an ICE vehicle. You got the engine, you got the transmission with its clutch, you've got the drivetrain going to the back wheels in this case. You might see the exhaust pipes here, and there's going to be a muffler down there somewhere. In an electric vehicle, the chassis holds the battery, and it might have an electric motor in the front, or one in the back, or two electric motors, one in the front and one in the back. And some cars will have two electric motors in the back and one in the front, and some will have 4 electric motors, one on each wheel. Okay, so what next? You should now have an idea of how ICE vehicles and EVs work, how they are similar and how they are different, and the advantages and disadvantages of each. In Unit 2, we will provide an overview of EV electronic control systems. We've seen a little bit of it here, but now we're going to go into depth with the control systems. So I'll see you then.